Okay, here's a quick run through of this skills check. So hang on, we're going to go pretty quick. A radius of the circle bisects a chord, then it is perpendicular to that chord. That sounds like a theorem. It sounds like always, but there is one small caveat. That chord cannot be a diameter. I suppose it could be a diameter. It could be perpendicular to the diameter, but it certainly doesn't have to be. So that makes it a sometimes. If it were a chord which is not a diameter, it would be an always. If it is perpendicular to a chord it bisects, it could be a sometimes, but here we have a sometimes. A diameter of a circle is a chord. That is always true, but the converse is not. When people talk about chords, they're talking about something that looks like this down here. If two chords are equidistant from the center of a circle, then they are congruent. That is one of our theorems. I will go with always on that one. Okay, this next problem talks about a common chord. This is the common chord. It is a chord both of my smaller circle and my bigger circle. By the way, looking at it, I think that the bigger circle is the one which has a radius of 26. So I'm going to draw this in and that in, my two radii. I will label at least one of them 26. I will mark them congruent to one another. And I will also draw in my other radii and mark them congruent to each other, at which point I have a kite. The hallmark of a kite is that one of the diagonals is the perpendicular, and that's all I really needed, bisector of the other one. Turns out that this one is bisected, either because of that whole thing with a kite, or because our more timely theorem, which says that if a radius or part of a radius is perpendicular to a chord, then it bisects the chord. They told me that that chord was 48. Now that it's bisected, I see 24. And looking at this right triangle, it is one of our special right triangles. I realize that 24 is hard to read. Maybe I will just draw this same triangle out over here with a right angle, a 24 and a 26. And those are both even numbers that can be divided by 2, at which point I would get a 12 and a 13. Oh, wait, we have a 5, 12, 13 triangle. And if it's been doubled, it is a 10, 24, 26 triangle. Still in that same family. They tell me their centers are 28 centimeters apart. Well, that diagonal was not bisected clearly, because if the whole thing is 28 and that is 10, then the remaining bit is 18. And let me now draw this triangle that we have a 24 and an 18. Well, 24 is 6 times 4, 18 is 6 times 3. We appear to be missing a 6 times 5. And although the mathematics did not care, it looks like I drew the smaller radius in the larger spot. No big deal. It wasn't a mistake. That's just something that we came to find from doing the math. Okay, and this next one, we have these 3 chords which are marked congruent, and part of our congruency bonanza says that if chords are congruent, then their corresponding arcs are congruent. So I'm going to mark them all X. Notice the measure of one of those arcs is what I'm looking for. And my 4th arc, the one which completes the circle, they tell me is 120 degrees. Well, a complete circle, which is 120 plus 3x, is always 360 degrees. So 3x equals 240. And x, what I am looking for, is 80 degrees. By the way, I put in my units of degrees there. I should have put in my units of centimeters here. As long as they're going to give me units, I should respond in units. Over here, an alternative way of doing it is by looking at all of these central angles. This one is 120. Again, if arcs are congruent, then their central angles are congruent. I guess chords are congruent, then their arcs are congruent, and arcs are congruent, then their central angles, or if chords are congruent, then their central angles are congruent. So I could have labeled these three things X as well. It is not a misuse of X because a central angle is equal to its intercepted arc in measure. This one is a run-of-the-mill one of these problems, which deals with a chord, a distance from the center, and those distances are always measured perpendicularly. And if a radius or part of a radius is perpendicular to a chord, then it bisects it. So we could label either of these things X. Remember that we're trying to find the length of the chord, so at the end of this problem, we're going to find 2X. The radius is 34. That is a good place to put in my radius and form that right triangle. It is 16, and again, we're dealing with centimeters from the center. And another one of these special triangles, thinly veiled. We have the 8, 15, 17. Well, this is the 8 times 2, 15 times 2, 17 times 2. So X equals 15 times 2, X equals 30, and the length of my chord is 60 centimeters. Okay. This next problem, I think, would be easier to do after we've done section 10.5. After we've done section 10.5, I could tell you right away that B, this inscribed angle, is half of that, that A, this inscribed angle, is half of this, and C is half of this semicircle. End up with a 30, 60, 90, get through it real quick. But let's do it this way. Let's draw in this radius. We'll mark all these radii congruent. Now I have a central angle, which is equal to the arc that it intersects. So if this is 120, then that's 120. It is supplementary to this angle, which is 60. And these two angles are going to be congruent because it's an isosceles triangle, sides then angles. Also, if sides then angles over here can help us to figure out what all the remaining angles are. We could use that some of the angles is 180. We can say that the remote interior angles are equal to the exterior angle on either side. Either way, we're going to end up with 30 and 30 over here, a grand total of 180 in that triangle, and 60 and 60 over here for a grand total of 180 in that triangle. Hopefully that's visible. One of my questions was to find measure of angle A. So at that point, we've done it. They told me that BC, that this chord has a length of 3√3. Well, that chord is congruent to this radius, obviously congruent to all radii, I suppose. And so if the radius is 3√3, then the diameter should be double that. It should be 6√3. And this time they did not give units, so I'm perfectly happy not returning them any units. Okay, real quick, just going through and listing what kind of things these are. BC, if they curved it like that, and we're talking about not the chord, but the arc BC. And if they don't specify what kind of arc something is, we assume that it is the minor arc. If they had done the arc DF, well, they would have had to tell us which one because neither of them are minor arcs. They are both semicircles. DE is a segment which starts and ends on the circle, and that makes it a chord. And the angle BAC has its vertex at the center. Therefore, it is a central angle. AF starts at the center and ends at the circle, or the other way around. Either way, it would be a radius. And DF is a chord, but they said most specific term, it is the chord which contains the center, intersects the circle. It is a diameter. The arc BEF, they tell us that E to say we aren't going the short way from B to F, we're going from B through E to F, and that is the long way. So that makes it not a minor arc, but a major arc. And finally, A is the center. That's all we've got. Thanks for watching.